everybody. So this is your tobacco auctioneer test review for test 3 in modern physics, fall of 2022. It covers chapters 4, 5, and 6. Most of chapter 6, not all of it. Most of these chapters, not all of it, from Thornton and Rex, your textbook. So basically the format of the test is going to be the same as the format for test 2. There'll be 10 multiple choice questions. You'll have to show your work for all questions. If you don't show your work and you get it wrong, you get no partial credit. But if you show your work and you get it wrong, then you will get some partial credit depending on how close you are to the right track there. So please bring a calculator and a scrap paper to the test. You're going to be allowed your 3-inch by 5-inch note card. You'll be given a constants sheet, so you don't have to waste your note card space on constants. And you'll be given tough integrals. So for example, if you have to integrate sine squared or something like that, I'd give you that integral from the tables. But you might be expected to do simple integrals like exponentials or sines and cosines, things like that. All right. So yeah. All right, so launching in, one of the first things that we talked about was the most important scattering experiment in history, which is the Rutherford gold foil experiment. In this experiment, Geiger and Marsden in Rutherford's lab took alpha particles, which are just helium nuclei, and they shot them towards a gold foil target. And what they noticed, and it was one of the most exciting results in history, was that some of those alpha particles were scattered at large angles. Now, most of them went through because the gold foil was super thin, but some of them got scattered at large angles, and that led them to the discovery of the nucleus. So the idea of the nucleus is that the positive charge and the neutrons, so the protons and neutrons, which make up most of the mass of the atom, are in a very dense central core, okay? And it's when the incident alpha particles basically have a really close collision with this nucleus that they get scattered at large angles. Otherwise, they're just running through empty space and they go straight through or are scattered at small angle. So let's discuss some of the language behind this. The impact parameter B is the distance in between what would be considered a head-on collision with the nucleus and what the trajectory actually is. So that's shown here, B. And the impact parameter is related to the scattering cross-section, where the scattering cross-section is the effective area of the target. And that is going to be sigma is equal to pi b squared, sigma being the scattering cross-section. Okay, because, of course, B is like the radius for the effective circle of that gold nucleus. Now, this B, this impact parameter B, can be given as the following: Z1 times Z2 times E squared over 8 pi epsilon naught K times the cotangent of theta over 2. Okay, so to define all these things, Z1 times E and Z2 times E are the charge in coulombs of the incident particle, like the alpha particle, that would be Z1 times E, and the charge of the nucleus, which would be, say, Z2 times E. Z1 and Z2 are the atomic number, or the number of protons, in those two objects. E is the charge on an electron, which in coulombs would be 1.602 times 10 to the minus 19 coulombs. Theta is the angle at which that particle gets scattered, as you can see here. Epsilon naught is the permittivity of free space, which is 8.854 times 10 to the minus 12 in SI units, and K is the kinetic energy of the incident particle. Okay? So there you go. Now, what you can do is, with this equation for the impact parameter, which is given there, you can calculate the fraction of the particles that are scattered at an angle greater than theta, okay? And so that fraction of particles that are scattered at an angle greater than theta is equal to nt times pi b squared. Now here T is the thickness of the foil, N is the number density of the targets, so the number of targets per unit volume in the foil. B is, of course, the impact parameter, okay, which is shown and given here. So you can calculate the fraction scattered at an angle theta, all right? So this was one of the major results from Rutherford's experiment, and he showed basically that in order to have them scatter the way that they scattered in his experiment, that the only way you can explain it is through that densely positively charged nucleus. So that was a big result. Okay, another thing that got covered in chapter 4 of your textbook was the Bohr model of the atom. Now it's important to understand that Bohr was trying to explain what was known about the hydrogen atom at the time. And one of the major things, experimentally, one of the major experiments that any good theory of the atom had to explain was spectra that you see. So if you take something like a hydrogen gas and you excite it by burning it or applying a high voltage or something like that, then instead of white light being emitted from the excited gas, you'll actually get specific colors of light. And if you pass them through a prism or a diffraction grating or something, you can see those as these discrete wavelengths or energies. So that's shown here. Okay? Now, there were scientists before Bohr that had done some work writing an equation that predicted what the wavelengths from excited hydrogen gas would be. And that's shown here in the Rydberg form of the equation. 1 over lambda is equal to the Rydberg constant times 1 over 2 squared minus 1 over n squared. Now here, of course, lambda is the wavelength of the light shown. And this is for the Balmer series, which is the visible light series for light. And that's why the first fraction here is 1 over 2 squared. And then n is an integer that starts at 3 and goes up in integer steps from there. So 1 over 2 squared minus 1 over 3 squared minus 1 over 4 squared, and so on and so forth. The Rydberg constant is 1.097 times 10 to the 7th inverse meters. Okay? So there was this for the visible light spectrum, and then of course there were corresponding equations that had a similar form for the ultraviolet, which was the Lyman series, and the infrared series, which is the Paschen, the Brackett, and the Fund. Okay? So it was known that in order to explain what was going on with the structure of an atom, you need to be able to take that theory and use it to explain these spectra, because that's one of the ways that we know what's going on with atoms. Okay? And so what Bohr did, his model, did that successfully. And so even though it's not 100% right, it still predicts some things very well, and it gives us a good mental picture. And so we still teach the Bohr model of the atom, even though it's not correct. Okay? Not completely correct. All right, so here was Bohr's model. It's a semi-classical model, so semi-classical, semi-quantum, okay? And he was pre-Schrodinger Equation, so this is pretty impressive. So here's what he did. He said that you have this dense central nucleus with a positive charge. For a hydrogen atom, it's just a single proton, so it has a charge of plus E. And that proton is orbited by the electron, kind of similar to how the planets orbit the sun. Okay? So it's got this circular orbit in its path around the proton. Since it's in orbit, then it's making that circle, then the centripetal force of the electron in its orbit around the proton, mv squared over r, is provided by that Coulombic attraction between the proton and the electron. And so that's, of course, given by Coulomb's equation, E squared over 4 pi epsilon naught r squared. Yet again, E 1.602 times 10 to the minus 19 in SI units. M is the mass of the electron. V is the speed of the electron. R is the distance in between the electron and the proton. Epsilon naught's the permittivity of free space. Okay? Now, this wasn't a new idea. The problem, though, with this model was the idea that it's a charge, right? The electron's a charge, and folks knew that accelerating charges would radiate away energy. And so the idea was it's an electron in a circular path. By definition, it's accelerating because it's moving in a circle. And so what that means is that it would radiate away its energy until it spiraled in and hit the nucleus. But what Bohr did was he said, okay, but that doesn't happen if it's in certain allowed orbits. And there's these certain allowed orbits in which the electron will not radiate its energy away. Now, those allowed orbits are when the angular momentum of the electron is an integer multiple of the fundamental constant h bar. Okay? H bar is Planck's constant h divided by 2 pi. H is 6.626 times 10 to the minus 34 in SI units. H bar is 1.055 times 10 to the minus 34 in SI units. Okay? So if MVR is equal to an integer multiple of h bar, it's a stable orbit. Okay? So MVR is equal to NH bar. From that, he then proceeded through a derivation where he showed that what that meant was that there would only be certain allowed radii of these orbits. Those allowed radii would be equal to the Bohr radius, which is 0.053 nanometers, times n squared, where n is an integer that starts at 1 and goes up from there. So it would be 0.053 nanometers, or 2 squared times 0.053 nanometers, or 3 squared times 0.053 nanometers. You get it, right? So these are the allowed radii of the orbits. In those cases, then the orbit will be stable and the electron won't spiral in towards the nucleus. So Rn is equal to n squared a naught. If the radii are discretized or quantized or only allowed certain values, then what that means is that the energies of these electrons will only also have certain values. It will be a quantization of the energy or a discretization of the energy, okay? So fixing the radius fixes the mechanical energy of these electrons in their orbits. That mechanical energy equation becomes, for a hydrogen atom and a hydrogen atom only, E sub n is equal to minus 13.6 electron volts divided by n squared. N here became known as the energy level, and also, once we get into quantum mechanics, the principal quantum number. N is for the hydrogen atom, an integer that starts at 1 and goes up from there. So for the ground state, which is the lowest energy state of the hydrogen atom, the energy of that electron is minus 13.6 eV. For the first excited state, which is n equal to 2, the energy of the hydrogen atom is minus 13.6 eV divided by 4, okay? And so on and so forth. So this energy level idea actually predicted the hydrogen atom spectra, and it was considered a great triumph for the Bohr model. The idea is that if an electron jumps from one energy level to another, then a photon of light, or a particle of light, has to be emitted or absorbed that has an energy that exactly matches the difference in between those energy levels, okay? So if it's sitting in the n equal to 2 and it transitions to the n equal to 1 state, for example, a photon that has an energy of 13.6 eV times 1 over 2 squared minus 1 over 4 squared will be emitted in order to conserve energy, and that's how that works, okay? And since this prediction actually correctly described the hydrogen atom, it was hailed as a great success because it described the spectra, and we still talk about Bohr's model of the atom today. Now, there were some things about it that were wrong. So first of all, it doesn't adequately describe what happens when you have more than one electron. Then it becomes a 3 or a 4 or a 5 body problem, and those are really hard to do in physics, okay? So it can't deal with multi-electron atoms. And there were also some problems if you started to look at the fine structure of the spectra. There were some spectral lines that were split off and things, and Bohr's model didn't describe that adequately either. So that had to come later, and for you, it will become in modern physics too, or in quantum mechanics when you take that, where we talk about the full Schrodinger Equation solution of the atom. But it's still hailed as a big triumph for Bohr. Now, you can extend to other atoms if and only if, you take this Bohr model and extend it to other atoms, if and only if those atoms still only have one electron. So you can't have multiple electrons, but you can have, for example, an ion, right? An ion which has one electron but more than one proton, okay? In that case, then what happens is those electrons are more tightly bound to the nucleus, which changes the radius. The radius now equation is Rn squared times the Bohr radius A naught divided by Z, where Z is the number of protons in the nucleus, and the energy levels also shift according to this equation, minus Ke squared over 2A naught times Z squared over N squared, okay? So in other words, you have to multiply the energy equation for the hydrogen atom times Z squared, okay, in order to get that happen, okay? Z is the atomic number, which is the number of protons. Okay, so that's a summary, fly-by-night summary of Bohr's description of the atom. Now, this model got verified in a few ways. One of them was, of course, it described the spectra, but there were people that were interested in what happens if it's not photons that are being emitted or absorbed that causes the jump in energy levels in atoms. Does the Bohr model still describe that? And so this was addressed by the Frank-Hertz experiment here. And in the Frank-Hertz experiment, what you have is you have a vacuum tube here that has a low pressure of mercury vapor inside of it. You have a filament here on the left-hand side, and currents pass through the filament, and through thermionic emission, electrons are kicked off. Through the tube, there is an accelerating voltage applied to the electrons that makes them accelerate towards what's called the collector, okay? And then there's a small repulsive voltage applied to the grid, which will reject electrons that have very little kinetic energy. It will repel them away. Okay, so if that accelerating voltage is below 5 volts, then the electrons didn't lose any energy and you had a straight up current to the grid. But if you brought the accelerating voltage above 5 volts, then what happens was there was a sudden drop in the current. So the results of the Frank-Hertz experiment actually looked like this, okay? So if you didn't have that bias voltage and nothing else was going on, you would expect a pretty much straight up plot of V is equal to IR, where you would have, with increasing voltage, an increasing current, and that would be it. But because of the repulsive voltage, the least energetic electrons were rejected. So what you would see is that the electrons would go through, they would collide with a mercury atom. It would be an inelastic collision so that the kinetic energy of the incident electron was transferred to the mercury atom. The mercury atom would use that energy to excite one of its outer shell electrons to a higher energy level, okay? That would cause the incident electron to lose its kinetic energy. If it had too little kinetic energy, then it wouldn't make it past the repulsive voltage and it wouldn't make it to the grid, and that caused the drop in the collector current versus the voltage. And this happened periodically, and the spacing in between these little dips was 4.88 electron volts, which was also, as they knew from the spectra, the energy that it took to excite one of those outer shell valence electrons to the next energy level up. And so this was hailed as a success. It showed that electrons, things other than photons, could excite electrons bound to an atom into higher energy levels, and it verified Bohr's model. Another verification of Bohr's model came from Moseley's work on characteristic X-rays. Now, as we studied before, X-rays can be created through bremsstrahlung radiation, right? Where you have a charged particle traveling at high speed, and then it hits a target, which rapidly decelerates it, and because accelerating charges radiate, it emits X-rays as it decelerates, okay? So that emits a continuous spectrum, which is known as bremsstrahlung radiation. But there's also X-rays that are created that are called characteristic X-rays. Now, these X-rays have very specific frequencies that change depending upon what your target is, okay? And so, for example, if you accelerate electrons with a given energy at any target, then you'll see kind of this kind of background increase and then decrease of the X-ray emission. So it'll be sitting on top of this hump, in other words. But there's also characteristics peaks whose energy changes depending upon what kind of target you have, whether it be made of gold or lead or whatever. Then that'll change these sharp peaks that you see in the X-ray spectra, and those are known as characteristic X-rays. Different elements have different energies of X-rays that act like a little fingerprint, used now, of course, to identify materials. So Moseley plotted what the energies of these characteristic X-rays were, and he linked those energies for those photons back to Bohr's model. And he came up with a couple of equations that he then published. One was that for what's called the K alpha characteristic X-ray frequency, HFK alpha is equal to 13.6 eV times 3/4 times Z minus 1 squared, where Z is the atomic number, and 13.6 eV is, of course, that ground state hydrogen atom electron energy. Okay? So, since he managed to link this back to Bohr's model, this was hailed as a great success, a verification of Bohr's model. He also used this data to predict certain elements that were missing from the periodic table. Okay, so he found some new elements that people then later discovered, and it was a great triumph. Okay, now Moving on to quantum mechanics. One of the most important things to understand about quantum mechanics is that none of it would be true if it weren't for wave-particle duality, okay? So the idea is that everything has wave-particle duality. Everything acts as both a particle and a wave, okay? The de Broglie wavelength for any particle, which has a speed of u, so this is assuming classical speeds, okay? Lambda is equal to h over p, where h is Planck's constant and p is the momentum. If it's a classical particle, that's h over mu, where u is the speed. So this is the de Broglie wavelength. Now, it's always true, okay? I have a de Broglie wavelength when I'm running, but it's not always helpful because sometimes the de Broglie wavelength is so tiny compared to the size of the object that you can't notice it. It's only noticeable when the objects are teeny weeny, like, you know, electrons and things like that, all right? This wave nature leads to important quantum mechanics rules and laws. One of the first ones of those is the Heisenberg uncertainty principle, okay? The uncertainty principle places a bound or a limit on how certain you can be about the position and momentum of a particle at the same time. That's one of them. And the energy and time of a particle at the same time, okay? So the Heisenberg uncertainty principle for the position-momentum relationship can be expressed as delta p times delta x, so this is the uncertainty of the momentum in the x direction, times delta x, is greater than or equal to h bar over 2, where h bar is Planck's constant divided by 2, or divided by 2 pi, and h bar over 2 there, so that would be h over 4 pi. Blah, sorry. Now this could be applied to any direction, so there's a delta px, delta x, and that's greater than or equal to h bar over 2. There's a delta py times delta y, and so on and so forth, okay? So this is the uncertainty principle. So basically this says that if you're completely certain about the location of the particle and delta x goes to 0, then delta p has to get really big, okay? And vice versa. So it places a bound on it. Now granted, it's a small bound, but it's still a bound. The inequality here, greater than or equal to, is because the Gaussian wave packet represents the minimum possible uncertainty, and all other types of wave packets are going to have a larger value than h bar over 2. So delta px delta x is equal to h bar over 2 for a Gaussian wave packet, and it's greater than that for everything else. There's also another form of the uncertainty principle for energy and time, and that's that delta E delta T is greater than or equal to h bar over 2. Okay? Now, there's some really super important consequences of this. Okay? One is that energy conservation can actually be violated as long as you don't do it for very long. Okay? And this is something that we get into when we talk about quantum tunneling here in a little bit. All right? But the Heisenberg uncertainty principle also places limits on how well we can know the mass of certain particles. Because when we take spectra to figure out what the energy of those particles is, and hence their mass, then there's going to be a certain spread or width to that plot, no matter how good our detector is. And that means that we're not going to fundamentally know exactly what the energy of the particle is. Okay, so I said that you have wave-particle duality, and that everything acts as both a particle and a wave. So if everything's a wave, then what's waving? Well, it turns out that what's waving is known as the wave function of the particle, which we, in most textbooks, call Greek letter psi, okay? Now, this is a probability wave. So what's waving in the wave function is the probability of the particle's location, which is kind of a mind-blowing statement. And if you haven't really internalized that yet, you might want to pause the video and think about it for just a second. But these waves are probability waves, okay? Now, you can find the probability of finding a particle in a particular range of regions or whatever by taking the wave function of the particle, squaring it, and then integrating over that region of space. So the probability, for example, that a particle is between x equal to a and x equal to b would be equal to the integral from a to b of the wave function squared times dx, okay? Now this would be the area under the curve for the psi squared versus x curve. Okay. Now, because the particle has to be somewhere with 100% probability, right, the probability is going to be equal to 1 if you integrate from minus infinity to infinity. And this is known as the normalization condition. Now, how do we find these wave functions for particles? Well, it turns out that you can solve for the wave functions for particles by using the Schrodinger equation. Now, the full Schrodinger equation is a time-dependent equation in 3 dimensions. But for your first introduction to this, we just stuck to one-dimensional potentials and we didn't look at any time dependence. So we didn't look at potential energies that changed in time. For that, we have the one-dimensional time-independent Schrodinger equation, and it's shown here in all its glory. Minus h bar squared over 2m times the second order derivative with respect to the spatial coordinate d squared psi dx squared plus u times the wave function psi is equal to e psi. Here u is the potential energy function, and it's a function, of course, in 1D because we're only considering 1D potentials. E is the energy of the particle, okay? And of course, h bar is Planck's constant over 2 pi, and m is the mass of the particle. This is the time-independent Schrodinger equation. It's only good for non-relativistic particles, all right? The Dirac relativistic equation covers other things, but that's more of a graduate level type of equation. There's some restrictions that form the boundary conditions for the solution to this differential equation. The wave function has to be continuous everywhere. The wave function's derivatives have to be continuous everywhere if the potential is finite. If the potential is infinite, it's imaginary anyway, so never mind, right? But we did solve one infinite potential well, so there you go. The wave function has to go to 0 as the position goes to plus or minus infinity. If it doesn't and it blows up, then that would mean that the probability was infinite, which is dumb. The wave function has to be normalized, which means that if you integrate over all space, the probability that it's somewhere has to be 1. The wave function can be complex or real, depending on the system. And the wave function has to be single valued. If it wasn't, then that would mean that there's more than one probability that a particle can be in the same location, which is dumb. Now you can do other things with the wave function other than just calculate a probability that it's in a region. You can also calculate what its expected the expected position, the expected momentum, the expected energy of a particle is using the idea here of an expectation value. So if you want to find the average position of a particle, for example, x, then what you would do is integrate x times that wave function squared, dx, and then divide it, of course, out by the integral of psi squared dx. Now, if you've already normalized your wave function, the denominator here is going to be 1 anyway. Okay, so you can ignore that if you have a normalized wave function. And the expectation of x is just the integral over all space of x times psi squared dx. Now, since psi can be complex, you'll often see this notation here with the asterisk after it. And that means the complex conjugate. So, in other words, x times the complex conjugate of psi times psi dx, that integral is going to equal your expectation value. For any given operator, some random thing that you want to know the expectation value of, what you do is you stick it in the middle here, okay? And you stick it in the middle because maybe it's a derivative or something like that, and you want it to operate on the correct wave function. So if it's some derivative, then you stick it here in the middle, and you take your expectation value that way, all right? Okay, now, we solved the Schrodinger equation for several different potentials, and I'll go over the solutions to each of those potentials in turn. Be aware that for your test, for Modern Physics 1, you are not expected to recreate these derivations. You're just expected to be able to know what those functions are and be able to know the energy levels and things like that for each one of the potentials that we covered so that you can use the information, okay? All right, so the first and easiest potential that we covered was the particle in the infinite square well potential. So the idea here is that your potential energy is 0 inside of a box, and the length of the box is L. So the box starts on the left at x equal to 0 and goes to x equal to L. Inside the box, the potential energy is 0, and outside the box, the potential energy is infinite. Of course, what that does is it confines the particle to the box. Now, a quantum particle confined to a certain region of space, remembering that particles are waves, and waves interfere with one another, what happens is standing waves form, okay? So you see these standing waves, and there's certain types of waves that form. You can see a wave with 1 hump that can form, or 2 humps, or 3 humps, that kind of thing, okay? These are the waves that form. Now, this is the wave function itself. Remember, the probability is the wave function squared. And so this is what you see if you look at the wave function squared. What these are probabilities of the particle's locations, which that means that for, say, the ground state here, n equal to 1, you've got most of your particles in the center, but there is a probability that some of the particles will be kind of over here, and none of the particles will be over here near the very edge. If you look at the n equal to 2 state, you'll see most of the particles falling here or here at L over 4 or 3L over 4. There'll be no particles in the center, not in the exact center, and then there'll be sort of a Gaussian or sinusoidal looking distribution of them on either side there. For n equal to 3, you'll see 3 areas of greatest probability of the particle's location, and so on. Okay? Now, what do the energy levels look like for this? The energy levels for the particle in the infinite square well can be described as E sub n is equal to h squared n squared over 8mL squared. Okay? Here h is Planck's constant, n is the energy level or the principal quantum number, and m is the mass of the particle, and L is the length of the box. And so if you plot what the energy is like, here you can see that even for the lowest energy state, the energy is not zero, which means the particle is bouncing back and forth inside the box, going left and right and left and right, and it's always got some kinetic energy. This is also a very non-classical idea. If you remember your ideal gas law, particles as they go towards absolute zero get very still, okay? But the particle in the box won't do that. It'll just bounce back and forth in the ground state, maybe going pretty fast even, okay? This is called the 0-point energy, and the 0-point energy is greater than 0. If it were 0, it would violate the uncertainty principle, so quantum particles aren't allowed to stop, right? Okay, so the ground state energy, or n equal to 1 energy, is E1, and then E2 will be 4E1, and E3 will be 9E1, and so on and so forth, okay? Now, the wave function for the particle in the box is the square root of 2 over L times the sine of n pi x over L. N is the principal quantum number, which starts at n equal to 1 and goes up at integer steps from there. You can tell because n equal to 1 is 1 hump, n equal to 2 is 2 humps, n equal to 3 is 3 humps, and so on and so forth. Okay? L is the length of the box here, and when the wave function is normalized, then the coefficient out front of the sine is root 2 over L. Now, the momentum values, since the energy is restricted, the momentum's restricted because when it's inside the box, all it's got is kinetic energy. And the energy, h squared n squared over 8mL squared, would be set equal to p squared over 2m, right? Because it's all kinetic. So then you can solve for what your momentum is, and it turns out your momentum, which is h over lambda for the particle, right? H over the wavelength of the particle, is nh over 2L, okay? So that means, of course, that the standing waves that form have certain restricted values. The standing waves can only form values of 2L over n, where n equals to 1 and goes up from there. All right? Okay. So that's the particle in the infinite square well. Another one that we covered was the finite square well. Okay? For the finite square well, the potential energy is 0 inside the well, and it's a finite value outside the well. We call the value outside the well U0 or V0, okay? And it's constant outside the well. The results of the finite square well wave functions look similar to the infinite square well wave functions, with one glaring exception. So you still see 1 hump, 2 humps, 3 humps for the wave function. However, when the wave function reaches the boundary, the wave function does not stop and go immediately to 0. Instead, it decays off exponentially. This means, of course, that the particle has a certain finite probability of being inside the well, even though it technically doesn't have enough energy classically to penetrate into the well. It can do so. The reason for that is the Heisenberg uncertainty principle. If you think about it, the thing has a kinetic energy which is less than the height of the well, all right? U0 is greater than K. What that would mean is that if it penetrated into the wall of the well, it would have a negative kinetic energy for a second. That's not going to happen. What actually happens is that energy conservation is violated for the amount of time allowed by the uncertainty principle. Delta E delta T is greater than or equal to h bar over 2. So energy conservation is violated for just a little tiny bit of time, okay? So we're violating it, but not for long, okay? Sorry, classical. Now, how far into the well the thing can penetrate is measured by the penetration distance, sometimes known as the skin depth, okay? So it's about how far the wave function extends past the classical turning point before the probability goes too close to 0. This eta is equal to, sometimes called 1 over alpha, which is h bar over the square root of 2m U0 minus e. U0 is the height of the well, E is the energy of the particle, N is the mass of the particle, and h bar is, of course, Planck's constant divided by 2 pi. All right? So you do get some penetration of the particle into the wall of the well. Another potential energy function that we studied, another potential that we studied as a solution to the Schrodinger's equation, was the harmonic oscillator potential. So in this one, basically, instead of a square well, your potential well looked like a parabola. Okay, this works well to model things like quantum bonds or atomic bonds. Okay. Now, the potential energy for the quantum harmonic oscillator is the same as the simple harmonic oscillator. U is equal to 1/2 kx squared. The result of solving the Schrodinger equation, which was a doozy, by the way, the solution was non-trivial to say the least, the energy levels that come out of that are E sub n is equal to n plus 1/2 times hf, or n plus 1/2 times h bar omega. Okay, here f is the frequency of oscillation, and omega is equal to the angular frequency. Of course, omega for any harmonic oscillator is the square root of k over m. All right, now, if you want to see the diagram for the energy levels, what this results in are evenly spaced energy levels. Yet again, there's a so-called 0-point energy. In other words, even at absolute zero, the particles still have some energy. The amount of energy is the energy of the ground state, which is 1/2 h bar omega or 1/2 hf. So even in the ground state, they're going to have a certain level of energy. And then it goes up in steps from there. So each energy level, each neighboring energy level in the harmonic oscillator is separated by an amount h bar omega. Because if you go, for example, 3/2 minus 1/2 h bar omega is h bar omega. Okay? So energy levels are evenly spaced here. For the other potentials that we solved for, they're not. Okay, so that's a different idea there. If you look at what the wave functions for the quantum harmonic oscillator looks like, you can still do the hump counting thing. This is your ground state with 1 hump. This is 2 humps. This is 3 humps, and so on and so forth. The big difference here for the harmonic oscillator to the other potentials, one of those things that's really hard for students to remember and easy to screw up, is that for the energy equation, E is equal to n plus 1/2 hf, n starts at 0. I'm sorry, the harmonic oscillator is the only one that starts at 0. But it starts at 0 and goes up in energy steps from there. So the energy levels are hf over 2, 3/2 hf, 5/2 hf, and so on and so forth, where E sub n is equal to n plus 1/2 hf, and n starts at 0 and goes up from there. Okay? So don't forget that. And the last potential that we studied was quantum tunneling on square barriers. Now, classically, of course, as we discussed for the finite square well, this is forbidden. It doesn't happen. But it does in reality, and I have a scanning tunneling microscope just down the hall that proves it. Okay? So what we solved for quantum tunneling was the probability of reflection and transmission through this square boxcar plot potential energy. So let's look at this function. Okay, so here's our potential energy plotted in the blue here. The basic idea here is that the potential energy is 0 everywhere except in the region x equals 0 to L, and in that region the potential energy is a finite value, which is V0. Okay, so some constant V0. So between there you have a constant potential. Everywhere else it's 0. The idea with that is that you can see you have this particle incident on the barrier from the left that has an energy less than the potential, V0. What happens is there is a finite probability that that particle will make it through the barrier and out the other side. This is called the transmission probability, or the transmission coefficient, and is symbolized by the uppercase letter T. The probability that it will make it through the barrier is given by T is equal to 1 plus V0 squared sinh squared kappa L over 4e times V0 minus e, okay? And this is all raised to the minus 1 power, so basically 1 over that. So this is the probability. Now, this can be approximated in a couple of different ways. One way to approximate it is just the straight up physics GRE way, which is the transmission probability is basically the same as e to the minus 2 kappa L. Or if you want to, you can leave the coefficients out front if you want. So in that case, if you want to be more precise, the transmission probability can be approximated as 16 e over V0 times 1 minus e over V0 times e to the minus 2 kappa L. Okay? Now, let's look at this plot here for a second and interpret what it means. Notice here that on the left-hand side, the amplitude of oscillation of the wave function is larger than the amplitude of the oscillation on the wave function on the right-hand side of the barrier. Remember that the wave function is basically the probability of a particle's location. So if the amplitude is smaller on the right than the left, it means that the particle is more likely to be on the left than the right. Okay? So that means that not all the particles that you shoot at this barrier are going to make it through. Only some of them make it through the barrier. Okay? Now, how do they make it through? What they have to do is tunnel through this barrier. Okay? And the thicker the barrier, the fewer the particles make it through. And the higher the barrier, the fewer the particles make it through. Basically, the probability of making it through the barrier is an exponential decay. Okay? That's dependent upon kappa and L. An exponential decay with kappa and L as a function. Okay? So this is the probability that's plotted here. Or the wave function. You get the probability from the wave function squared that's plotted here. Okay? All right. So remember that sinh is a hyperbolic sign. And remember that, I can't believe this isn't shown. Hang on just a second. Hey, I can't believe that wasn't on the slide. I'm sorry. So here it is now. Kappa is the wave number. And so kappa is equal to the square root of 2m times v naught minus e, okay, all over h bar. So the h bar isn't included in that square root, okay? It's in the denominator as a standalone. So that's our wave number. And so you can see that there's a dependence on the probability of transmission on the height of the barrier through the v naught here. There's also a dependence on the mass of the particle. So if you have a supermassive particle, then that's going to give a large value of kappa, and the probability that makes it through isn't very likely. And it also depends on the width of the barrier here. The thicker the barrier, the less likely it is that makes it through. But see here, it's not a zero probability, okay? All right. Now, I wouldn't try it for you. Your mass is way too big. You're never going to make it through that wall. But quantum particles, electrons, things like that, they do successfully tunnel. And one of the examples that we gave of that was the scanning tunneling microscope. Okay? So that's it. That's the last of the quantum potentials that we solved for the Schrodinger equation. Okay? So to sum up, basically, particles are waves too. The fact that particles are waves, too, gives rise to lots of strange behavior, including the uncertainty principle, okay? The Schrodinger equation is the way to solve for the wave function, which describes the wave that a particle has, okay? So the wavelength is lambda is equal to h over p, but the wave function psi gives you the amplitude of the wave function, too. And the amplitude of the wave function actually gives you the probability that a particle is located in a specific region, okay? Now, we solved Schrodinger's equation, which is something, by the way, that is a first principles equation that cannot be derived, although we did justify it, okay? So it's a first principles equation that cannot be derived. This equation, given a potential, will tell you what the wave function is like, okay? So it'll tell you, predict for you, what the probabilities of the particle's location are given the potential. All right, so that's what we've done. Right? That's what we've done at the very end of class. Whew. Okay, I hope that's clear. I hope it makes sense. If you have any questions, let me know, and good luck on your test.